Welcome back to your physics buddy. In our last session, we built a visual foundation for how magnetic field and forces work. Today, in lecture 2, we are taking that infusions and applying it to a rigorous Wilson-Buffa and Leo college physics framework. Mastering the AP physics exam requires more than just knowledge or more than just knowing formulas. It requires the ability to solve high-level problems from respected university-level resources. Today, we are tackling specific case studies and mathematical challenges that test your precision with magnetic magnitudes and vector direction. We'll be looking at how charges behave in varying field strength and orientations. If you need a refresher to the right hand rule or basic properties of magnet, make sure to review lecture 1 before moving forward. Following this, in lecture 3, we'll expand these concepts to earth magnetism and transformers. This is where the conceptual knowledge meets mathematical mastery. Grab your calculators and your copy of Wilson Buffa. Let's dive into these advanced problems.
Is a branch of physics which deals with charges in motion. So whenever charge is in motion, it can create magnetic field around itself, and the concept and the phenomena associated with those magnetic fields is called magnetism. Here we talked about magnetism from two aspects. First, from uh, the application part, like where we can actually use it, how can we use this magnetism effect from for our benefit, as well as we also talk about Earth's magnetism. What are the key roles of Earth magnetic field in preventing us from any possible situation? So they also play a different role, and that is also we're going to talk about. So we'll define what are permanent magnets, what is magnetic poles, and we can also call it as magnetic dipoles. Then we talk about magnetic field direction, which we already know that how we can calculate it. Apart from this, we'll calculate the magnetic field strength, we'll talk about force, we'll see some application part, which is mass spectroscopy. We talk about current carrying wires, how can they produce magnetic field around itself. Then the important aspect of this, which is electromagnetism. So we'll be defining here that how electric field is correspondingly responsible for the production of magnetic field, and how magnetic field is correspondingly responsible for the production of electric fields. We'll talk about that as well. At last, magnetic materials and the thing which I told you about Earth magnetic field and Earth magnetism. We'll talk about that also, which comes under the unit called geomagnetism. It is a subunit of subunit of magnetism, and we'll talk about that also. So the scientist who laid the foundation of this particular unit was Nikola Tesla way back in 19th century. After that, there was Pierre Curie. He was also the foundationers of this particular unit or particular branch of physics. So they did different experiments and they did different findings to evolve and let us know how magnetic force exists. So let me just give you a little bit idea about that how everything is being noticed. So it was a small story, and I guess you should know it. It will let you remember the concept for a long time, I can say. So there was a, you can say there was a person who just went on with his kettles to feed those kettles in a area where there's a lot more magnetic field around that place. What exactly happens there is that he was wearing a boots, and in those boots there was an iron nail. So while he was walking through walking through the lane, what he found is that there is a little bit difficulty while walking, and initially he has no idea what is exactly the reason. But later on, it becomes the foundation that the mountain or the place where the person was living with those kettles was basically a magnetic region. So the iron nails in his shoes got attracted towards the magnetic field and they started creating attraction, which made it difficult to walk. And this laid all the foundations of magnetism. Then we need to understand this thing. Conductors are the only one which can create magnets. If we have conductors with ourselves, then we can talk about this fact that it can repel as well as attract other metal around it. So let us just try to understand this magnet thing, that what magnet is. So magnet is basically an object which has this capability of attracting another metallic object around itself or getting attracted with those metallic objects as well. What made magnets different from normal conductors or normal other elements is that the arrangement of domains, or you can say the arrangement of poles. The magnet has different poles at the ends, at the corners generally, and because of those poles, we do observe that they can create magnetic field from itself. So here you can easily see in this diagram, that is 19.1, which is a diagram of bar magnet. So what we have did here is around a bar magnet, we just sprinkle some iron filling, or you can say some iron powder around itself. So we observe that the iron powder is not something which is placed itself randomly. It has reorganized itself, and it has reorganized in this way. So this particular diagram becomes the foundation, or you can say the first basic idea about the field lines, that how magnetic field lines look like, how we can actually observe them. So these field lines, they are coming out from North Pole. They're supposed to come out from North Pole and go into South Pole like that. So what they do is they form a continuous curve. These are the continuous curves. So these continuous curves represent that magnetic field is something which forms closed loops, just like that. Although it is coming out from north and going from south to north inside the magnet, just like that. So one of the features of the common bar magnet is that it has two centers of forces, you can say, which are known as poles at the ends, and they are something which we can refer as positive and negative, just like in case of charged particles. So here we can simply see that what is the behavior of north and south pole. If we bring like poles each other of two bar magnets, they have tendency to repel each other. So this shows one thing, that if the two bar magnets of same pole are brought to each other, like the like poles are brought to each other, they will repel, whereas the unlike pole will attract. So we can easily verify this, and we already know this thing through different activities we have done in the previous grades, we can say. Then we defined the direction of magnetic field. So magnetic field direction is somewhat similar to the direction of electric field we define. Just like electric field, it is associated, or you can say it is directed from positive to negative charge. The magnetic field is something also which is defined the same way. Suppose this is a bar magnet having two poles. So magnetic field will be like that, from north to south. Inside the bar magnet, it is from south to north. It is denoted by B. We already know this. We already know that it is a vector quantity, again, a very important part. And also, the most important part here is all the concepts we learned in electrostatics associated with electric field. All those similar concepts are exactly applicable here as well. This is the most important part you need to learn. So all the derivations which we did, they were quite similar to those of which we did in electrostatics. So there is not much difference here. We can simply say that. So you can say that how you can actually identify this. Suppose you have a bar magnet. It has north pole here, south pole here, and we know magnetic field will be going from north to south. Suppose we come up with a compass. So when we come up with a compass, the compass has a needle in it. So it will align itself in the direction of magnetic field, this needle. So this will align in such a way that the needles, this part will be directed towards the north and this part will be directed towards the south. Similarly, when we talk about compass from Earth surface point of view, so if we try to observe in the direction of north, so whatever direction that compass is going to show, it is going to show us the direction of magnetic north pole. It is going to show us magnetic north pole direction. Again, remember the geographical north, which we generally observe here. This is not magnetic north. Geographical north and magnetic north are completely opposite. We'll talk about it. So that is important. That what does exactly compass shows? It shows the direction of north pole by aligning itself along the direction of field. So here we can say the most important part, the magnetic field is defined in terms of magnetic force exerted on the moving electric charge. Just like we defined that electric field is force per unit charge. So what does it mean? It means how much force a charged particle is experiencing when it is in magnetic field. That will give us magnetic field. Similarly, if we have to define the magnitude of magnetic field as well, we can say it is the force experienced by the charged particle in motion, or you can say moving charged particle. Whereas in case of electric field, the charged particle is supposed to be at rest. That is the difference, and we should know that difference. Then we talked about magnetic field strength. We talked about magnetic forces. We already know magnetic field strength can be calculated Using this is the magnetic force formula. So I already informed you, I already told you that force is given by QVB. We can also write it as QV cross B. We can also write it as QVB sine theta. So all those are the formulas for magnetic field only. As there is nothing associated with the cross product we have to learn, so we can simply say magnetic field associated with a particular region has capability of exerting a force of about QVB sine theta in terms of magnitude. Similarly, we can see the direction of motion of charged particle as well. So if there is a charged particle, it enters into the magnetic field, it will go like that. Like the force will act on the charged particle in such a way that it will rotate it, or you can say it will turn it with an angle of 90 degree. It will depend upon that how much angle it will get based upon the strength of magnetic field, based upon the motion, or you can say direction in which it is traveling. So all these factors are responsible for calculating the direction of motion of a charged particle under the influence of magnetic field. Always remember there will be a force which is acting against the direction of motion. That is important. That's why it got curve. That's why it got displaced by some angular displacement theta. How can we how can we measure magnetic field? We can measure magnetic field in Tesla. So it was given after the name of Nikola Tesla because he was the person who actually found out magnetic field and saw so many applications. Let me just tell you, Nikola Tesla was the person who wanted to create wireless electricity. This was the motto of Nikola Tesla. And you can't imagine if he was able to succeed in creating wireless electricity, it would be like so much beneficial to us. Like if you just imagine all the current which travels in a home, it generally carries through wires. And Nikola Tesla was the person who wants to create wireless electricity. It is a huge thing. As of now, also, if you try to think that we create wireless electricity, it seems to be a dream. But he was the one who was trying to do that. But although you know how sad ending we got when he died, you should learn about Nikola Tesla.
Okay.
He was the great person. So the force, we got to know that force is nothing but QVB. We just try to remember that only. If there is an angle between the motion of the charged particle and the direction of magnetic field, then whatever angle is there will multiply that angle in terms of sine. The right hand rule is the rule which is used to find out the force acting on a moving charged particle. So again, these are the examples to show this. So suppose there is a magnetic field which is acting along this line. Charged particle is moving along this way. So force must be acting upward. And that is the reason we saw in the previous example when charged particle move in this way, magnetic field is going in this way. The force acts in upward direction and the charged particle started moving in 90 degree to its initial position, or you can say initial motion of direction. So here also it will go like that because of the magnetic field. So right hand thumb rule, or you can say right hand rule will help us to understand. So how we can find out in whatever direction the magnetic field is, just try to uh, face that direction in terms of palm, or you can say you can also use a forefinger to put the direction. Thumb will represent the direction of force, or you can say thumb will represent the direction of motion of the charged particle. That was the initial direction of motion. In whichever direction initially it was moving, just place your thumb in it. Forefinger will give us the direction of magnetic field. Try to put the forefinger in that way. And ultimately, where in whichever direction your palm is pointing out, this will give us the direction of force. So that is the thing, that is the formula which you can remember it, which you can use to find out the direction of magnetic force. So there is a one question, I guess we should try this question out. The question says a particle of charge minus 5 times 10 to the power minus 4 coulombs and of mass 2 into 10 to the power minus 9 kg moves with this speed. So here we have given charge, here we have given mass, here we have given velocity. It enters into a uniform magnetic field of 0.2 Tesla. We have also given magnetic field. The question is which way the particle deflect as it enters into the field. Now this is something you should tell. Think about it. The given figure given figure side view is given to us. Charge particle enters in the positive x direction. Field is directed in the positive y direction. So charge particle was going like that. Field is set up like that. So in which direction the force is acting on the charge particle? Think about it. You can simply see the diagram. The diagram is given, side view. You just have to refer the diagram. Thumb will be placed in the direction of motion, as I told you. Forefinger will be placed in the direction of magnetic field, and the direction of palm will give us the direction of magnetic force. So just tell me, what is the direction of magnetic force here?
It would be to west.
When we are talking about directions in terms of x and x, y, z, so you have to answer in terms of x, y, z. Because
Okay,
when we
so
consider, yeah,
okay, so positive y then.
positive y is already is the direction of magnetic field. Just look at the diagram.
Okay,
As I told you, when we apply this rule, the palm will be going to give us the direction of force. So this positive z will be representing direction of force.
okay,
This is the direction of velocity. This
yeah.
is the direction of magnetic field. So force will be acting perpendicular to it in this way. So the question
So
is,
okay,
yeah,
is there positive v also?
yeah, it is given. V is in positive x direction. See the question. Mass moves in the direction positive x, uniform magnetic field in the positive y direction. It is given. First part says, what is the direction of deflection? The direction of displacement will be positive z. So it will go like that. Now the question is, what is the magnitude of force on the particle when it is in the field? How much force is going to act here? So we know force can be calculated by qvb sine theta. The angle between the velocity and force is something we need to understand. So velocity and force must be acting at 90 degree in this case. So sine 90 is going to be 1. So we can simply put the values and get the answer. So just solve it once. You just have to put the values into the formula and you get the answer. You
Yeah,
have given charge,
yeah.
you have given, yeah.
Negative 1 to the power of uh, times 10 to the power of negative 9. That's what I'm getting.
Okay. What is the velocity you have substituted? What is the charge? Just check it out. And it should be 0.1 newtons. Although you can check it out as well. Now, the third part. What is the radius of the circular arc that the particle will travel while in the field? So we have to understand this thing that charged particle enters into the field this way, and magnetic field is outward. It is represented by dot. Always remember that. Sometimes in order to represent a 3D diagram in 2 dimensions like that, like this, so we'll use dot and cross. Cross is representing field is outward, and this is also known as out of the plane, whereas dot is representing into the plane. So suppose this is a case, field is going into the plane like that. So we'll use cross here. So if I have to draw this plane xy like that, we'll represent cross here. Similarly, we'll also represent dot in order to represent field coming outward. So here the diagram is drawn in this way that the field is out of the plane, out of the page, coming outward towards you, and velocity of the particle is given into it like that. So the thing is, we have to find out the radius of the circular arc. So what is the radius of the circular arc? That is what we have to find. So how can we found it? So we know that the force acting inward because of the magnetic field is going to be QVB. But there must be some force acting outward, which is going to be mv square by r, and this r will give us the radius. That is something we need to find here. So we will substitute QVB in terms of mv square over r, and from here we can find out that r is nothing but mv over qb. We'll substitute the values of mv over qb, and we'll have the answer. We'll have the radius of the circular arc. Do that also. Put the values and tell me the answer.
Negative 4,000. That's what I'm getting.
Negative 4,000. It cannot be negative. If you're considering the magnitude of charge, so magnitude of charge will going to be positive. Whereas here the negative charge is representing the nature. We don't have to consider the nature here. But 400 is going to be a big thing. It is 2 centimeters. Just check the values which are substituted, as well as check the calculation. It's 10 to the power minus 9, it is minus 4. It is going to become 10 to the power minus 5. 10 to the power minus 5, 10 to the power 3. It is going to be 10 to the power minus 2, which is what we have written here. If you solve this, then or you can say 5 times 0.1 is 0.5 by 1, which is going to be 2. 2 times 10 to the power minus 2. It is correct. 2 centimeters, we can say this. So this is how we are supposed to solve this question. Got it?
Okay.
After that, we have to see the application part, that where we can actually use this magnetic field in human beneficial thing. So we do use in mass spectroscopy, which help us to create different things, which you can say mass spectroscopy is something, the application which involves working of different devices, which involves magnetic field in it, which have capability of storing charge. They can use that. So the first thing where we need to understand, a charged particle moving in magnetic field experience magnetic force. This is something we have already understood. This force does what? This force actually displaces this particle by a small amount, which depend upon its mass, charge, and velocity, as we saw in the diagram, as well as in the relation. So let us try to understand that how magnetic force plays different roles in common appliances like machines, instruments, and you can say sometimes television, electronic devices. All of them make use of it. So earlier, or you can say late 20th century, we do used to have these kind of television. Do you saw such televisions? Did you saw these kind of televisions?
Yeah.
So these are actually the televisions, and these televisions make use of these cathode rays, or you can say those spectroscope, which actually creates image. So this was the best invention we have at that time. visualizing something and then watching it in real, you can say, motion. So that was a big achievement for us later that time. First, they came and then we got somehow, you can say, cameras and everything. Those every advancement in real life is because of magnetism. Every advancement. Before the discovery of this magnetism thing in the real world, the development was like you can say crawling. Development was not with taking place with that pace. But once we got this information, you can say knowledge about magnetic part, magnetic effect of charged particle, it just changed the scenario, complete scenario. And later on, in the early 19th century, early 20th century, when we had this thing with us already, we discovered photoelectric effect by the Einstein. So Einstein did the photoelectric effect thing, and that thing and the magnetism part already, which we discovered, those two things just changed the scenario. Like it just changed the world, complete world changed after that discoveries or inventions. So that was the reason why Albert Einstein was considered as the best, or you can say the most important scientist in the discovery, or you can say in the development of humanity over a period of time in terms of technology. We do used to imagine so many things at that time that there will be some car kind of thing, there can be some television kind of thing, there can be some fan kind of thing, like whatever appliances that can come to your mind. Those were just, you can say, in dreams when we have no information about these things. But when we got to know about magnetism part and quantum, we can say physics, we got to know more about that. It just changed the whole world. The technology we are advancing as of now is like at the top. Although there is so many things to be discovered yet, because what we can imagine, I believe, we can create. It's all about imagination and what you can imagine. It's depend upon that. So here in this kind of televisions, we do use cathode ray tubes. It is kind of vacuum tube, which was not discovered a lot more time ago, hardly 100 years ago. We just got to have this. The basic operation of these oscilloscope and you can say old-fashioned television picture tube is basically given. The electrons are emitted from the hot metallic filament and accelerated by a voltage applied between the cathode and anode in an electron gun arrangement. In one kind of the design, these tubes use current carrying coil to produce magnetic field. So these are placed in such a way that they do use magnetic force, magnetic field in such a way that the charged particle can be accelerated from its actual motion. Accelerated means if we have more charged particles falling onto the fluorescent screen, like what is this exactly? This is a fluorescent screen. What does this do? When a charged particle strikes it, at that point, it got, you can say, some sort of light, some sort of bright light. So n number of charged particles when fall onto this fluorescent screen in such a way that they can create an image, and that image is something we do observe on the screen. So what we have to understand here is the speed of the charged particle, which is going to get accelerated from this electron gun, or you can say the with whatever speed it is going to get out of this electron gun. When it falls on the surface, it will fall and brighten that spot. Suppose this spot, it got brightened. Also, the speed will define that what color it is going to show in the fluorescent screen. And when lots of charged particles, or you can say lots of electrons, falls onto this, you can say screen, they will create an image, and that image is something which we can see on the screen. In today's world, we are so advanced out of this technology already because we do have LEDs, OLEDs, which are like very thin, and still they can create a so much better image on the screen. So all was possible because at some point of time we had this thing with us. We know how to get advancement because human brain is something which always tries to, you can say, evolve something out of anything. Curiosity is something which this particular kind of species has different from others. I'm talking about humans. Whereas all the other species which are there on Earth, They do have all the basic senses, but they don't have that curiosity. So that is what made us different from other species, and that is why we are dominating here on this earth, not the other species. Although there are, you can say, millions of other species present on Earth. So this is also called velocity selector and mass spectroscopy, because here also we do the same. We accelerate the charged particle, and that charged particle will travel as per our need based upon, or you can say, on the function of speed. We just give the charged particle defined speed, very high speed. We can do that. So that velocity is also, let me just give you the idea, it is equals to electric field over magnetic field. Whatever electric field you have created, divide that electric field by magnetic field, and that is going to be the speed the charged particle will have. Again, the most important part, it will not depend upon the charged particle's mass size or whatever it has. Any physical significance of charged particle will not going to affect with this thing, that how much speed it will get if we just put into this electric and magnetic field combination. So that instrument is called spectrometer. As I told you, field is electric field per unit magnetic field. You can remember this factor. And sometimes this electric field is created by a battery. So it is again the velocity which will get, it is again going to reduce. Similarly, we do have different things here. You can also calculate the mass of a molecule in a mass spectrometer based upon that relation only. Now let us just talk about what is the magnetic force acting due to a wire carrying current. So I already give you the idea about this fact that whenever there is a current carrying conductor, it must be carrying current in one direction. So in order to understand that what is the direction of force, or you can say what is the direction of magnetic field around that conductor, you can simply calculate by using right hand thumb rule. So if you just put your thumb into the direction of current, the fingers in whichever direction it will curl, it will give us the direction of magnetic field. So that is something we already saw, but if we try to calculate the force here first, whatever we talked about, that was about field. But if we try to understand that how much force it is going to apply, so just remember, in the direction perpendicular to the direction of current, force will act. So this current carrying conductor carrying current in x-axis, it will apply the force in y-axis if it is experiencing magnetic field in z-axis. So magnetic field direction will decide whether the force is going to act upward or downward. If this field is acting this way, so force must be acting downward. So current and the direction of magnetic field will decide in which direction it is going to apply the force. And I already gave you the relation for the force as well. It is going to be IBL sine theta, whereas theta is going to be the angle between magnetic field and the length of the conductor, you can say, direction of flow of current element, which is called IDL. That is something we use to define this particular law from the calculus point of view by writing IDL. This IDL is known as current element. So current cannot have a direction because it is a scalar quantity. But if we just put current, or you can say just understand that current is something which is carrying in this conductor, and this conductor has some length dl. So this current carrying element IDL will have certain direction, and that direction we are using here to find the angle. Whereas length and magnetic field has an angle, it is very, you can say, uh, non-physical thing to accept, because length is something which is scalar, we already know. Mass is something which is scalar, we already know. Current is also something which is scalar. So two scalar quantities can never have a vector product. So vector product is something which is already seen in two vector quantities. So here I and L, they both are scalars in terms of, you can say, their physical significance. But this current carrying element. We define this current carrying element to define a vector quantity hidden in this relation, which is current carrying element. So that's a different thing, or you can say a little important as well to remember. Now let us try to understand what is the magnetic force on wire at the equator. So if there is a wire and if we try to just understand that how much magnetic force it will be experiencing due to the field of earth, again it is going to be calculated using the same relation. So here is a question and let us just try to answer that question. It's a conceptual question, but yes, we should answer such questions. So question says magnetic force direction is something we have to find. So question says because a current carrying wire is acted on by a large magnetic force, it would seem possible to suspend such a wire at rest above the ground using Earth's magnetic field. So the question claims that it is possible that we can already suspend a wire using magnetic field, Earth's magnetic field at the equator above the surface of ground. So question says, assuming this could be done, consider long straight wire located at the equator. So we just have to assume all these things that we can put the wire on the equator above the Earth's surface. What would be the current direction to be to perform such a feat? Up, down, east, west. So if this is a surface, are we supposed to put the wire in such way, in this way, in this way, or in this way? In which direction we should do that? So how can we answer this? That is an interesting part, and let us try to understand it. So according to it, answer can be, or you can say the explanation can be given this way. So magnetic force direction must be upward, that is away from the Earth's center, because gravity acts downward. The Earth's magnetic field at the equator is parallel to the ground. So whatever Earth's magnetic field is there, it is always parallel to the ground as it is shown here. So field must be opposite away from it. Sorry, field should be parallel to the Earth's equator like that. So this is the equator and we just put a wire here. So along the direction of it, field must be like this way. So we just try to understand it here. It is drawn in this diagram. So the Earth's magnetic field at the equator is parallel to the ground and point north. Because the magnetic force is perpendicular to both the current and the field, the current cannot be down or up. Because if it is up or down, the field will exert a force in such a way that it cannot sustain at the above surface. It has to be like that. Eliminate the first two choices to decide between east and west. Simply choose one and see if it works. Like suppose the current is to the west. So if current is to the west, and we try to understand that how force will be acting, so it shows that the force acts downward. And if force acts downward, and we already know that mg, that is weight, is acting downward, so this is going to be incorrect. So the only option left is option 3, east. So if we choose the direction of wire towards east, so force will act upward, weight will act downward, and these two forces will cancel out each other and we can balance it. The second part says if it is possible, calculate the current, or you can say length as well. Assuming mass of wire is given as 30 grams, magnetic field is 4 times 10 to the power minus 5 Tesla, because this is the Earth's magnetic field, you can imagine at that point. Length is given as 1 meter. So if we just put the value of length in that direction, the weight which it is going to balance out must be ILB. or you can say the value of this weight is already given as 30. So the current in the wire must be 7.4 times 10 to the power 3 amperes. And this current is huge. Like this current is very huge. Let me just give an example. So if you just observe your phone charger, you must have seen the supply of current it gives out of it. What is the output? Have you seen it? Have you seen the ratings of a charger?
Hmm?
Any charger. Have you seen the ratings of your charger, like any charger?
Yes,
What is the rating of a charger?
15 watts,
And what about the current output?
3 amps.
So just try to imagine that your phone only needs 3 amperes of current. And the wire, if you want to make it suspend in air under the influence of Earth's gravity only, Earth's magnetic field only, the current passed through should be 74,000, 74 hundreds, you can say. And the phone needs only 3 amperes of current. So how you can say big this number is? That is what I'm trying to explain.
Okay.
Similarly, we understood how if there is a coil acting, having current, some current passing through it, if we suspend that coil in a uniform magnetic field in such a way that force is acting anti-parallel to the opposite coils, anti-parallel to the opposite arms of the coil will rotate, and that rotation will be going to produce torque on it. And what is the basic function of torque? The basic function of torque is to rotate. Like, let me just show you something. You must have seen this, I guess. If you just place a coil between the magnetic field and just spin it, it will continue spinning. And that continuous spinning is because of the magnetic force which is acting in such a way that it is acting in the opposite ends and making a couple. We already discussed this word. Like the forces which are opposite in direction but equal in magnitude, they forms couple, and they have this capability of rotating a disc or a coil, or you can say, I would say, a ring or a coil, because coil can be a ring sometimes. It look like a ring sometimes. Let me just show you this thing.
A
Just see this.
rectangular loop PQRS of length L and width W, suspended perpendicular to a uniform magnetic field B bar. Current I flows in the coil in the direction PQRS. On applying Fleming's left-hand rule on side QR, the magnetic force F1 equal to IWB turns out to be perpendicular to QR and to the magnetic field. Magnetic force F2 on SP, that is equal to IWB, turns out to be opposite to F1. As you can see, forces F1 and F2 are equal in magnitude, opposite in direction, and have the same line of action. Hence, the resultant effect on the loop is zero. Similarly, force on PQF3 equal to ILB is same in magnitude, but opposite in direction to that of force F4 on RS. Since the line of action is the same for both forces, they have no effect on the loop. Now, let the loop's normal make an angle theta with the magnetic field. Forces on SP and QR are equal and opposite to each other, and they have the same line of action. Hence, they produce a net force equal to 0 and net torque also equal to 0. Magnitude of the force on PQ is equal to the magnitude of force on RS, but they don't have the same line of action. Hence, they produce a couple due to which the coil tends to rotate in the clockwise direction. From triangle PSN, sin theta is equal to Pn by Ps. This gives the distance between the forces Pn equal to W sin theta. Net torque acting on the coil is equal to the product of magnitude of force and the perpendicular distance between the forces. WL is equal to area of the loop. Hence, torque on the coil is equal to IBA sin theta. Let A bar be an area vector of magnitude A normal to the loop. By curling fingers of right hand in the direction of thumb gives the direction of A bar. Net torque can be written as IA bar cross B bar. IA bar can be replaced with a vector called magnetic moment. Magnetic moment of a loop is the product of current and area vector. Torque on a loop is simply M bar cross B bar. This result.
So these specifications, or you can say the mathematics involved to explain the expression, involves vector most. But here what we have to understand is it is IAB sin theta, where A is the area, B is the magnetic field, I is the current flowing through the loop, and sin theta is the angle between the force and length. So we understood this, how force, or you can say it can produce, how force can produce torque, how it can rotate a coil, and this rotation ultimately produces electricity. That is the most important application we found of magnetism, because when it rotates, it produces torque, and torque ultimately leads to the formation of electricity. Very interesting thing, and that thing is also used in calculation of current, like the galvanometer we have, voltmeter we have. They use the same application of rotation of coil, and that rotation of coil ultimately produces current, and we can calculate that magnetic field also. It is capable of producing that much current. So high rotation, or you can say high RPM, produces more current, low RPM produces less current. So as fast as we can make it, it will produce more and more current. So let us keep it till here. In the next class, we'll complete this lesson. We'll discuss electromagnetism part. We'll discuss how this will produce current, how magnetic field produces current, and how current can produce magnetic field. We'll understand this aspect and understand, or we'll can say unlock the new dimensions of this branch of physics, which is called magnetism. Although we discovered all the formulas before as well, but again, those were just the mathematical aspect. The physical aspect, or you can say the application part of these topics, to understand that thing is more important than this whole application part, because than this mathematical aspect, because that is something which anyone can do. But understanding application part and creating something new, it comes out of curiosity, and that will only work if you know the basic aspect of all of these things. So let us just keep it till here. In the next class, we'll talk about more.